Hi, in this video, we want to take a look at fitting models to aerial data. Okay, so aerial data is when we have data coming from like regions, polygons, such as states, counties, neighborhoods, countries. All right, and what we've got going on is that I have data for each of these regions, and I want to do statistical analysis on this data. Now, something I need to be mindful of is that before I can get to this point of fitting a model, I need to go ahead and I need to determine which regions are connected to each other, how they're connected to each other, that is the weights, and then I need to choose like my modeling format. Okay, if I make a poor choice along the way, the whole thing is going to be meaningless garbage coming in. And after I do that, I need to do my hypothesis testing for global and local autocorrelation. So now, spatial autocorrelation, we're going to cover two approaches to this. Our modeling is going to be based off of spatial autocorrelation. Our two approaches you can think of as regression on top of regression, and then the other one is conditional probability on top of regression. All right, so the example we're going to work through is a leukemia example from Applied Spatial Data Analysis with R, Chapter 9, Areal Data. Here are the authors of the book. I've modified the code for this presentation. You can get the original code from their website here. And if you're a UCF student, you can download the book for free. All right, so let's jump down to the example. All right, so I've determined what regions I'm going to have as being connected to each other, as who are neighbors. They don't actually have to be geographic neighbors to be neighbors. I have control over that if I want to do something different. Most of the time, the author here and the packages in R prefer row standardized weights, so that, you know, a weighted average. So I've set it up my neighbors, I've set up my weights, I've done my hypothesis testing that I conclude I have autocorrelation going on. Now I actually want to model that autocorrelation so I can get further information out of it. We have two approaches. It's going to be regression and then conditional probability. Now, of course, we would prefer that our spatial observations be mutually independent, but frequently this isn't the case. So I'm going to have a more complicated model than what I would prefer. Remember, independent, identically distributed is always what we want, but we're assuming we don't have that situation here. And I don't have points on the ground data. I have data for the regions and the polygons that I'm working on. And we're doing this after we conclude that we have autocorrelated data. All right, so often relevant covariates just are not in our data set. So there's predictor variables, covariates that I should use in the modeling of my target variable, but I don't have it. And that's just a realistic aspect of statistics. If I'm getting underperforming models, that could lead me to believe, hey, I'm missing something in here. Can I go back and collect that data? What we're going to do, we're going to use spatial autocorrelation on model residuals to account for variation. All right, so our game plan is first, I'm going to do a covariate regression model with my target variable. Then I'm going to look at the errors on that regression model, and then I'm going to do autocorrelation, either like a regression autocorrelation or a conditional probability. Now, if I misspecify my model, which includes the neighbor aspect and the weights and model structure, I can get garbage in, garbage out. And so we have to be very mindful of that. We have a lot of choices to make to be able to get a good result at this point. This is a major pitfall. All right, so what we're going to take a look at, we're going to think about doing a transform on our data. And some things we need to think about as we work through this is how will we handle non-constant variance? Think about adding a missing covariate or dropping one, changing the functional form of a covariate that we have, and we can change the distributional representation of the response variable. All right, so we can start using transforms, and the same things that we can use in regular linear regression to get better models there, we can apply here. All right, so let's go ahead and talk about spatial statistical approaches. All right, so we're going to basically go in and we're going to model our target variable on using our covariates, and we've already reached the point that we believe that we do not have independent and identically distributed, and we're going to go ahead and take the belief that we do not have independence because we have correlation between neighboring areas. Now, if I'm eyeballing the situation on a map, it's hard to really figure out what is the spatial autocorrelation and spatial differences. So let's go ahead and talk about, at this point, using a transform and weights to address heteroscedasticity. So I observe non-constant variance in my data. I want to use transforms and weights to get a better model. All right, so before we get to that though, let's talk about like our setup. For the two types of models that we're going to do, we're going to make the assumption that y is equal to some average plus a stochastic term. So here mu is the vector of area means. This E is the vector of random errors. We're going to make the assumption that E is multivariate normal with mean zero and a variance matrix. We'll say that y is linearly dependent on the covariates. That is to say that y is equal to x transpose beta. There should be a plus E there. And V accounts for the correlation between areas. All right, now, if y is not multivariate normal, what we're going to do, we're going to use a transform to make it into approximately multivariate normal. All right, so what we're going to choose to do for this data set, the leukemia data, is that we're going to use a log transform on the counts to get something that's approximately normal. We see that we have skew right data, and when I have counts, frequently square root is a good choice, but here the author chose log, which is definitely a reasonable way to go, especially if it's highly skewed. So for their transform, here y is the actual target variable that we're interested in, but it's so skewed to the right, non-constant variance, that, you know what, let's go ahead and do a log transform on this. So remember, logarithms must have positive values in them. Remember that from college algebra. And so I'm going to add 1, and I'm dividing by n, and then I'm multiplying by 1,000 just to make the numbers a little bit easier to work with. Then I take the log of it. Boom, that is my z. All right, so that's going to be our target variable. So roughly speaking, I'm going to say z is the log of leukemia counts. Now, to model this in the linear regression aspect, we're going to use the inverse distance to the closest TCE site. So that's going to be the exposure. We're going to use the proportion of people aged 65 or higher, percent age 65p, and the proportion of people who own their own homes, PC town home or PCT own home. All right, so let's go ahead and just right off the bat, since this is a teaching video, we're going to do a linear regression model. Now, this is always a good step to go in to get, to start with regular regression before we start messing about with the spatial aspect. So here's my formula. I'm going to say that z depends on the predictor variables we just talked about. Here's my data. Now I'm interested in the residuals. So I'll go ahead and pull those off. And now let's go ahead and take a look at the summary of our linear model. So this step here was just to append the residuals onto my data frame. All right, now I look at this, And I see that exposure is not statistically significant, but percent age 65 and over and percent owned home is. All right. So, that right off the bat, we might want to consider dropping this. But from subject matter knowledge, we know that exposure to the TCE site makes people more likely to have leukemia. So for the moment, I'm going to keep this in. And as I work with this, as I work through the project, maybe it will become statistically significant. If it doesn't, I'll go back in my project and remove the variable. Here we can see that we don't really have a great R squared at this point, but it is statistically significant. So we're seeing that there is something there, but it's not strong enough for the purpose of prediction. All right, so now we want to address spatial autocorrelation in our residuals. All right, so how we're approaching this is that first I am doing linear regression, then I do autocorrelation on the residuals. One thing that I potentially could do is I could fit them at the same time. If I was to fit them at the same time, there would be comparatively lesser emphasis on the regression part and relatively greater emphasis on the autocorrelation part. By doing regression first, then working on those residuals afterwards, the regression aspect picks up as much variance as it possibly can, and tries to leave, if it can, tries to leave nothing for autocorrelation. And so because of the sequence of events of how this is actually computed, we have to be mindful that our autocorrelation is going to appear smaller than it would if I right out the gate did autocorrelation. And so whatever I do first is what's going to have that will be the situation where it gets the most emphasis. So potentially I could try to do an autocorrelation, then do a residuals linear regression that would put more emphasis on the autocorrelation. Now the fitting of that model will be kind of complicated, but we could definitely do it. All right, so what we want to do is we want to work with our spatial autocorrelation, and we want to see if a regular linear model is insufficient, because if it isn't, then we want to incorporate the spatial. So right now I've got just a linear regression model. I have not considered who's neighboring who in terms of the residual, in terms of the model yet. All right, so always, our previous choices have a huge impact on our results. And so I made choices about the neighbors, the weights between neighbors, and the model structure and the covariates up to this point. If I've made a poor choice, it's going to impact everything going forward. So now let's go ahead and use Moran's I-test for residual spatial autocorrelation. This is a global test, and the previous video addressed that. And so here I'm doing lm.moran test, and I see that it's statistically significant. So I believe that there is global autocorrelation going on. So now I want to do something about it. All right, so now we're going to check for spatial autocorrelation. We're going to use maximum likelihood instead. So this is just going through and doing the same thing, but in a different manner. Now, what method I'm going to use for this alternative approach is that the rows need to be row standardized. My listing did not work out on our markdown. I apologize for that, but my bulleted list should be, first of all, this method requires that weights are row standardized, weighted average. The target variable has mean 0, and the target variable has been detrended. So we've taken care of the covariates aspect first. And this is Apple, missing a P. So it's the approximate profile likelihood estimator. It's a simultaneous autoregressive model for spatial dependence parameter. So when it says simultaneous, that means that we're doing regression, like a regression-like autoregression approach. So it employs a corrective term using eigenvalues of the spatial weight matrix. And this will not work well for large number of observations because of the computational load. And so here we get a 0.21, very different result. Actually, this is our likelihood, yeah. All right, so now let's do a spatial simultaneous autoregression model. All right, so what we're going to do, we're going to take the family and the weights arguments for our spatial autocorrelation, autoregressive model, and we're going to fit by maximum likelihood. And we're using dense matrix methods. All right, so when we're talking about this material, something we have to be mindful of is if I have dense matrices and a lot of data, it's going to be computationally heavy. And so if I have like a lot of neighborhoods that I'm modeling on, and I have and everybody is a neighbor of everybody else, this can be computationally difficult for our system to handle. When you see me say dense, that means that neighbors are connected to, everybody has a lot of neighbors. Sparse means that everyone has very few neighbors. Now, if I have a sparse matrix, larger number of observations can be handled, but we also need to set the other parameters in the call. So here we're doing generalized least squares to find the single spatial coefficient value, which the R package calls lambda. And this is found by search using optimize to maximize the log likelihood. All right, so here we can see we get a pretty close lambda. So, so both of these give me estimates of the global autocorrelation. All right, so now let's do simultaneous autoregressive models. Okay, so what I'm doing is I've already built a regression model of my target variable on my covariates. I'm taking the residuals from that, and I want to see, hey, do I have autocorrelation on there? I believe I have autocorrelation, so now I need to fit a model. So what we're going to do is we're going to fit a model on the error terms of this form. So think of this as the residuals on the linear model. What I'm going to do is I'm going to do a regression on all of the residuals with everybody else. And then there's going to be, it's not going to mathematically be perfect. And this is going to be the residuals after I incorporate the linear model residuals autocorrelation. And so now so I've got like two levels of residuals going on. I have residuals for linear model, E, and then take care of spatial autocorrelation. After I do that, I still have another level of residuals after that. We're going to assume that these are multivariate normal with mean vector 0 and a variance covariance matrix, where our variance covariance matrix is going to be diagonal. All right, so now think about that. That is saying that after I've taken care of autocorrelation, there is no more relationship between regions. That's what we're saying when we say covariance 0. Now, maybe not independent, but covariance 0, which statistically, operationally, is as strong as we can realistically get things in real data. Now, if you look at this formula here, I have to have it that the regression term of a E residual with itself has to be, the coefficient has to be equal to 0 for this to be a meaningful equation. We cannot regress a value on itself. I mean, we'd get perfect correlation. It'd be really great and wonderful if that made sense. It doesn't make sense. So this is just saying that I'm doing regression on each linear residual with everybody else, in terms of everybody, all of its other neighbors at least. Now, frequently, something that will be done to make things cleaner, make it easy, have us have fewer parameters to fit, is that we'll say that we have a constant diagonal matrix instead of a varying diagonal matrix. All right, so now let's take a look at the formulas we get. All right, so here we get, this is our model of the target variable. So now I'm going to drop this into the situation. I should have a space here, a little bit of an error. There should be a space. So now if I put this in matrix format, drop that into up here, I see now that this is my version of Y. This tells me that the second level residuals is equal to this matrix formula. All right, and we're saying that the expected value of Y is X transpose beta. Our variance of Y, of course, here is the variance term, the random term in Y. Therefore, we're using its covariance matrix in that. And so here is our variance of Y, standard formula for random matrices. And when we have epsilon, it has a constant diagonal, then this simplifies nicely. Now we can parameterize this to incorporate that autocorrelation coefficient, that lambda that we found. So what I'm going to do, I'm going to say that B is equal to lambda times W. Lambda is our spatial autocorrelation coefficient. That is the statistic that I use to represent how much autocorrelation we have. Then W is going to represent the spatial dependency. Frequently, this will be symmetric, but not necessarily. And so when I do that, the formula changes just a little bit. All right, so now let's go ahead and run an autoregression model estimation. And you will notice that now exposure has gone down in terms of p-value. And the other two that were already statistically significant still are. P-value for the overall test. Now, when we're building multiple models of multiple forms, the AIC will be important for us to compare models in choosing a final model. All right, so let's go ahead and just take a look at how do I get the lambda out and how do I get the p-value? Well, all I do is I take the object I have for my simultaneous autocorrelation model and I just grab the lambda off of it. Now to get the p-value, I have to run summary. Then I have to take likelihood ratio. Then I take p-value, and I got it. All right, so now let's go ahead and append what we've got to our spatial polygons data frame. So here I want simultaneous autoregressive trend and simultaneous autoregressive, the stochastic part. All right, slap that on there. And of course, I want to visualize this. And I'm using the same visualizations that are covered in a previous chapter of the textbook. So let's take a look. All right, so with the trend, we see the trend part. So this is from the predicted values. And here, this is the autoregressive part. This is the stochastic portion of it. All right, so this is the that E business is over here. Now notice that something interesting is happening over there. This is darker than I would like. We would like to see, less on this one. We would like to see our trend accounting for more if possible, but doesn't work out. All right, so now this is our spatial trend. And this is our spatial stochastic component, where this is our model, and this should be a transpose. I'll have to fix that in a moment. I'll fix it before class. All right, so now what we're going to do is I look at this, and I'm not 100% satisfied. I think I could do better. Well, could I take into account the population size? I probably should do that. So what I want to do, I want to change the weights using the pop8 column in my spatial polygon data frame. So this is a column of data in the data frame, and I want to incorporate that into the model. All right, so here I'm going to do a regular old linear model. I've got the weights going on, and let's see what happens. Now, something should jump out at us about this is that you'll notice that, all right, statistically significant, statistically significant, and statistically significant. Now, we've done 2 models prior, and P exposure was not statistically significant. Now it is. So once I put in weights, all right, I can see that, hey, that's probably an important aspect. R squared improved, but not by much. And I can see that the overall F statistic of the linear model is statistically significant. So I feel like I'm going in the right direction. So once again, I'm going to visualize the residuals. This is basically a repeat of what I've already done. So here are the residuals of the linear model and the residuals of the model that uses weights. And overall, I can see that I have less extreme colors when I use the weights. That gives me the feel that a weighted model is a better model for this situation. And let's go ahead and run Moran's I test for global spatial autocorrelation on the residuals. And all right, so here it shows p-value of 0.3, so we conclude that there is no spatial autocorrelation on the weighted linear model. That's interesting. That has a huge impact on what's going on. Now, if we believe that there is still a simultaneous autoregressive autocorrelation going on, then I can still proceed. Let's see what happens. Let's explore what's going on. And what I'm going to do is I'm running the same code I ran previously for the spatial autoregression. But here the difference is, once again, I'm using weights in my model. Can I get a better model going on? And then, hey, look at that. Statistically significant, statistically significant, statistically significant. I'm feeling like this is the better model to go with so far. Now I can use the AIC in each of these in deciding which model to actually use. So let's go ahead and visualize. Now notice that the residuals on the stochastic part have practically disappeared. Like everything's very muted. So I feel like this is putting more on trend, less on residual aspect, and I feel like this is a better model for us. All right, so now that was going through and taking the first level residuals and then doing autoregression on the residuals spatially. Now, another approach I could do after I do my linear model, I could do a conditional probability model on my residuals, where residuals are depending on other residuals. All right, so for this approach, we're going to take a normal approach. So we're going to say, hey, that the residual at a particular location, given all of its neighbors, so here, think neighbors. Basically, I'm worried about all of its neighbors when I say this, is going to be conditional normal, where I'm using the CIJs to represent the dependence relationship between different regions. And to run this, I'm doing the same function, the same trick from spatial reg package, but now I'm using, instead of SAR, I'm going CAR. SAR is for simultaneous auto regression. CAR is for conditional auto regression. And so here we see P exposure once again is not statistically significant, but it's not horribly away from it either. So it's near that borderline. We see that percent that own their home is no longer statistically significant, but it's on that borderline. Maybe things will improve if I put in the weights. So same trick for being able to get the coefficient of spatial autocorrelation. Now, if I put in weights, same trick I did above, over and over and over, I'm putting, population size for the weights. We see that everything now is statistically significant. And here is my AIC to help me decide which model I should actually go with. Now let's talk about actually fitting the spatial regression models. These can be computationally heavy because I have a covariance aspect between the regions going on. All right, so the function that we're using from spatial reg package uses maximum likelihood. It first finds the value of the spatial autoregressive coefficient. Then it fits the other coefficients by generalized least squares at that point. All right. So remember, in the computational flow, whatever comes first is the one that is going to get like the most emphasis in my modeling. So the linear regression gets the most emphasis, then spatial autoregressive coefficient, then the other coefficients will get more emphasis. Whichever comes, whatever parameters come in first in computation are going to account for as much variance as they possibly can. Therefore, I can expect the other ones to get smaller if I was to switch the order in the fitting. All right, so now as I'm fitting, I've got different methods I can use. First of all, I could use eigenvalues for dense matrices. This is not feasible for large number of regions with a lot of neighbors. Matrix J for sparse matrices. And they want it to be symmetric or similar to symmetric. So remember, when I say similar, that is a conjugacy aspect. That's mathematically similar matrices are conjugates of each other in terms of a matrix algebra point of view. And this uses the matrix package. Matrix package uses Cholesky decomposition. This is good for sparse matrices. W needs to be symmetric or similar to symmetric. So like W and S for the styles are good to go. LU decomposition is alternative for sparse matrix decomposition. So if you have experience with Cholesky or LU, go with the one that works for you, one that you feel more comfortable with. We have Chebyshev for approximate log determinant, and we have Monte Carlo also. Now, the most demanding part of the optimization is computation of the Jacobian, the log determinant of this. So I minus lambda W, and then taking the determinant, then I take the log. As n increases, the use of eigenvalues is computationally not feasible. All right, so why is that? Well, how it works out. So notice that lambda appears in every single time. What is going to happen is that it's going to go, hey, let's check out a particular lambda value, do the computation. Change the lambda value, do the computation. Change the lambda value, do the computation. Change the lambda value, do a computation. Keep on doing this over and over and over for all of your potential lambda values. It's doing this over and over and over. So if I have, if this computation for any one lambda is relatively heavy, and I'm doing it for a lot of different lambdas, then this is going to be computationally even heavier and won't be feasible for a lot of situations. All right, so here is how we're approaching this. And so remember that if I have I minus lambda W, this is equivalent. So this determinant is equivalent to the product of 1 minus lambda and then the eigenvalues of W. We're using some similarity of matrices to pull this off. Here we're saying B is a symmetric weight matrix and D is a diagonal matrix where we are rescaling the sum along the columns. So W is D times B, and then W star is the square root of D conjugating W, like this. Now, at this point right here in the textbook, there is a slight error. The negative sign is missing from the textbook. It's a small slip. It does make a difference in the computations. I believe that the author intended for the negative sign to be on the right. I'm not 100% sure, but I think this works out just, my playing around, this worked out the way I expected to when I did my explorations of manual computations. All right, so something to be mindful of is that because W star and W are similar matrices, therefore they have the same eigenvalues. This is true. So here I'm conjugating W. Therefore, it doesn't matter what I conjugate with, I will always, as long as I have full rank, I will have the same eigenvalues. And so W star and W have the same eigenvalues. And so if W star is better to work with in the computations, that's the one I'm going to go with. And so now let's go ahead and use the decomposition to get the computations that we want. This is better when I have larger matrices. And here's my summary of what's going on. I see that we have statistically significant across the board, looking nice, looking nice. Notice that I did use weights in here. I've concluded that using weights is a good way to go. Here I'm using simultaneous autoregression. And so everything's looking pretty similar. I just had a twist on how I did my computations. Now, as I work through this, we can control the log likelihood aspect of this. So what we're going to do, we're going to specify, or we have the opportunity to specify either how many lambdas are computed, or we can actually say, I want these particular values. All right, so what happens by default under the hood if you don't touch it, Spatial Reg package is going to check the lambdas from the minimum eigenvalue, 1 over the minimum eigenvalue, to 1 over the maximum eigenvalue. Reverse the order of that, by the way. And it's going to check values in that range. So here, it's going to check, in this situation, it's going to check from -0.3 to 0.15 for potential lambda values. Now, what I could do, if I wanted to, the ll-prof, I could specify the sequence that I wanted, or I could specify the number that I want. I could say, hey, I want this range here chopped up into 100 different points, and then check those 100. So we can either specify the number where it'll chop up this range, or I can specify the actual values I want, either way. Now let's go ahead and plot it to see what it looks like. So here I'm just using, regular base R plotting, and here the solid line is our weighted simultaneous autoregressive model. So it's a linear model, then autocorrelation on the residuals on the linear model, and then here is our star. So we have our weighted up top, and then we have our unweighted dashed line, and we can see that my peak is a little bit greater than 0.0. And we can see that for every single possible lambda value, we're seeing that the weighted model is performing better. So you know what? I feel like the weighted model is definitely the way to go. Now we also have the option of using spatial moving average if I want. And we can control what's going on. So here, if I want to use spatial moving average, I just put family equals SMA. I get pretty similar results, honestly. All right, well, that's all I've got for you. Take care and goodbye.